Okay, well, we have a couple minutes before class. Any questions before we start? Lots of stuff that in the handout. Remind me of your name.
Scorby, Sophia.
Got it. Gotcha.
So when it comes to terms, would the conservation of mass itself be statistical knowledge, but the law of conservation of mass be intellectual knowledge? Because like you could see that, but then to put it into like terms.
Or something similar. In other words, physical laws. If you're asking generally, are physical laws part of sensible knowledge or intellectual knowledge? I would say intellectual knowledge. The understanding of the general principle. General aspects. Yeah, that's a good question. Okay, so there's a lot to digest. It's really simple stuff, but when you ground physics in this very basic stuff, then it makes it much more meaningful, much clearer when you're talking about things, what it is that you mean, because you're grounding it in the things that are really understood by us very well, common ordinary things. And so it would be best if you could have started your study of physics with this grounding. But we're in a more advanced class now, so we can't spend a lot of time on this basics. I would love to spend more time. Once you get into it and you learn it, you know, it's a little unfamiliar now. Once you get into it and you learn it well, it's very natural. Really a great way to understand physics. Makes it much more intelligent, much more meaningful, much clearer what it is we're talking about. And so it's wonderful when you can do that. So this is very brief. I really wish we could spend a little more time on this. I do have, let's see, Professor Padilla is teaching Physics 1220 using the mechanics textbook, and he is spending more time on this basic stuff for his class, first semester class. If you're interested in seeing a little fuller, a little more time spent on it, discussing it, watch his Zoom recording taking this semester, so that's a possibility. Or just talk with me. That's more time on it. Mr. Rutland had it in high school, so it's more familiar to him. This corner, more familiar to him than most of you. So he's been through this material several times actually. So he's got that benefit, and we talked about it a little bit in the E&M the second semester. But the entire second semester was built on these basic principles. So there's a nice book also called Kids' Introduction to Physics. There's actually 2 volumes. And I highly recommend those. Those are great gifts for small, simple, you know, brothers and sisters, even grown-ups actually. Despite the title, it's really this basic physics none of us have really understood very well, and so this is a great introduction to it. The first volume just talks about impetus and mass and force. The second volume goes into electricity and magnetism and quantum mechanics, physics of the atom. Nice, really nice book. Big font. 60 pages, I think. Maybe the second one's a little bit longer. It's really nice, makes a nice gift, and and you can read it and it'll help you to understand how to talk to your friends, family about physics, what your interest in physics is, and why, and you can explain things better, you understand what's here. Okay, so I'm going to talk first about impetus. Come on in. Okay, so let's imagine that we have a sheet of ice, and I have a hockey puck this and it's resting on the ice, and I give it a kick, punch it. And so as a result, it's sliding on the ice. Well, the question is, why does it keep moving?
Lack of friction. And
Okay,
also
so,
inertia.
all right, so first answer was lack of friction. So something that's not there is what keeps it moving? That can't be right.
Inertia.
Yeah, the inertia is, let's hold on to the inertia as a possible answer. There's confusion there. Yes, sir.
Momentum.
Yeah, or properly impetus, right? So there is a property of this body that keeps it moving. Now force had something to do with it. I punched it. So force has something to do with it, but I'm not punching it anymore. It's still sliding. So there has to be some property that this has now that it didn't have before, because it wasn't moving before. And now, after I punch it, it has something that's changed in some way. Something has been altered so that it will now keep moving. If I have two hockey pucks and I punch one of them, this one is sliding, the other one is staying at rest. This one has something that one doesn't have. And so the cause, there has to be a cause of this change. It's changing place, there has to be a cause. And it's not force because I'm not pushing it anymore. There has to be something that's changing this, continuing to change this, responsible for the persistence of that motion.
Well, I also wanted to, I thought about something like, I don't know how to explain properly. Let's say you're on like the sheet of ice is on a train that's moving.
Right.
It's not accelerating, but it's moving at a constant velocity.
Sure.
So if you don't hit it, the puck will stay still relative to you, but relative to the ground, it'll be moving.
Yeah, so you're bringing up the question about relativity, really, what you're bringing up, and I don't want to get into that right now. But the answer is still basically the same. Okay. So, but let's just stick with this because we've got a couple of things we need to establish first. So impetus is what causes it to move. So the question is, what is impetus? Again, we're moving from generic to specific. So the most generic thing you ask is it a substance or a property? It's a property, not a substance. Property of massive bodies. Okay, is it, and then you go down the categories. Is it a quantity? No. It's a quality. So it's a quality of the body. And it's that quality of the body which moves the body in a fixed direction and at a fixed speed. And plus it's altered in some way by a force. Okay, very simple. Okay, now let's suppose I have two hockey pucks and one's big, the other one's small, and I give them both the same punch. I give them both the same intensity of the impetus. They're not going to move the same way. Right? But how is it going to be different?
The smaller one will go faster.
Right, the one, yeah, that's right. So the small one goes faster, this one goes slower. Okay, now they differ again by some property. They have the same impetus, but they differ in some way that makes them move different. So what's that?
Mass.
That's the mass. So having just gone through that simple exercise, forget everything else you've heard about mass, because it was all confused. Just think about this. What does that say that mass is?
The resistance to movement.
It's the resistance to the action of the impetus. Not the resistance to moving, but the resistance to the impetus. Okay? So let's be more precise. Generic to specific. Is mass a substance? No. It's a property. Is it a quantity? No. It's a quality. It's the quality of the body that determines it's a kind of resistance to the action of its impetus. Yeah.
So after the hockey puck is moving, does mass continue to resist the action of the impetus?
Yes. Yeah, you've misunderstood. You've been taught mass is resistance to acceleration. That's not correct. It's also it is primarily resistance to the impetus, and secondarily, it will also be the resistance to the acceleration, but that's a secondary effect. Primarily, it's the resistance to the impetus itself.
Could you also describe mass as like, let's say you have like the same two hockey pucks of equal mass. If you hit one of them, it'll move at a certain speed, but if you attach a string to both of them and you hit one of them, then the force of the hockey puck will be distributed equally among the hockey pucks.
Right. So for a body with parts, you can say, or a group of substances, you can say that the impetus is distributed in proportion to the individual masses.
That's just the way I think of visualizing mass. It's just everything is made up of parts. Not those parts can be atoms, those parts can be molecules, those parts can be like even elementary particles.
Yeah, things have parts. And you can think of the impetus shared by the parts in proportion, but don't forget, you still have a whole, and it's the impetus of the whole that we're talking about.
Yeah.
Okay, so impetus and mass. Now, go back to inertia. You heard that word inertia, and that's what you are familiar with. Inertia is a confusion. And this is being more precise, because sometimes when we say inertia, we mean impetus, and sometimes we mean mass. For example, when I said, why does the hockey puck keep sliding? The answer, somebody said inertia. Properly, it's impetus in that instance. But then if your mom asks you to push the fridge to another part of the kitchen, and it takes a lot of force to get it to happen, that's the mass. You have to give it a lot of impetus, and it has a lot of resistance to that impetus. So to get it to move, you got to give it even more impetus. If it's moving much. So inertia is a confusion. And so we're being more precise here. Right? The word confuse. To confuse means to take two things that are properly separate, different from each other, and fuse them together in your head. That's a confusion. When you're confused, you've got two different things going on, at least two going on. And the way to resolve the confusion is to make a cut between them. Be precise. Cut precisely between the two things, exactly separating them, not cutting off part to be with something that shouldn't belong to. So you make the cut exactly where the two things are different from each other. So impetus and mass are the precise understanding, precise principles at work in locomotion. Inertia is a confusion. Let's fix those two things together. So I can go on more about that, but and the other textbooks that you will see, this confusion is rampant. It's everywhere. A lot of people get confused about inertia. They're studying inertia. A lot of people, when they're reading the textbooks about inertia, they get confused. And they're not sure why. And the teachers can't help them out because the teachers don't have this precise understanding either. And that's the reason why so many students struggle with inertia, because it is inherently a confused concept. And that's why it causes problems. So you put inertia aside, because it is a confusion, and start trying to understand things in terms of impetus and mass. You'll have a much easier time understanding and being able to explain things. Okay, so the next thing is force. So force is, again, a quality of a body that is its ability to change the impetus of another body. So that's how it worked here. Case where I gave it a punch, I gave it impetus it didn't have before. If there were friction present, the friction would be another kind of force that would drain the impetus from this body. And so that's, you can understand friction as a force in that. So very generally, those are the things we talk about: impetus and mass and force. So in the example, this is what you want to focus on when you talk about like the example in the homework, most of you didn't get it right. For today's homework, the discussion of throwing a ball up in the air. So you gotta really understand this. So I'm going to send out the solution after class today. Study the solution. I'm going to go over it again right now. Okay, so let's start with the one that was in the write-up. I'm going to drop this. Okay. And I want you to explain in simple physical terms what's going on. This is very simple stuff, right? You should be able to explain to your grandmother, maybe who's never had any math, what's going on. So don't give her equations, just talk about stuff. So use these terms: impetus, mass, and force. Okay, so when I let go, it has no impetus. That's just for a brief interval. But there's gravity acting downward on this, which gives it downward impetus. And so as a result, it starts to move. And all the time that it's starting to fall, gravity is still acting on it. Gravity, the force of gravity is steady, continues to act downward. So it continues to gain downward impetus. And it just keeps getting faster and faster as a result until just before it hits the floor, it's got the greatest amount of it. It's really simple. Don't make it complicated. Yeah.
So how do you work mass into that? Because it doesn't have much of an effect when it's just gravity.
It does, but there's two things going on there. So we're going to talk about gravity in just a minute. Gravity is a special kind of force in the sense that mass comes in a different way in gravity. But suppose to, yeah, so let's hold on to that a minute, okay? There's really three different kinds of mass that we talked about. So we'll come back to that. So just generically though, there's a force that's acting on it, and the resulting speed is determined by its mass. In the case of gravity, the force is proportional to the mass as well, which makes it then the resistance and the force are balancing off each other. They're both proportional to the mass. And so there's a kind of aspect where bodies with different masses will fall in the same way. Peculiar to gravity. All right, so now I want you to get this down because it's definitely going to be on the test on Monday. If something like that or some other similar situation. Let's suppose I throw it straight up. Yes, ma'am.
Test on Monday?
Yes, test on Monday. It's in the schedule, isn't it? I believe so. All right, well, we check that. It's the test on this basic stuff on Monday. We double check. So you got the scheduled assignments from Canvas. Everybody able to find that? There's a file called scheduled assignments. I don't see it. I see assignments for chapter 0. Right under the main. Oh, there you go. Under the main, under files, there's a scheduled assignments. And excuse me, test is on Wednesday. Thank you very much. Okay. Okay. So let's suppose we throw this thing up. Now, how does it modify what's going on? So in this case, the impetus is upward, right? It's given the upward impetus by my hand. So now it has upward impetus. The difference now is that the impetus is opposite to the force. The force is still downward, it still acts steadily, but it's in the opposite direction. So it's going to remove the impetus from this body because it's in the opposite direction. And then once the impetus has been drained, it stops briefly. But now the force of gravity continues to act, and now it will start gaining downward impetus, just like we did when we dropped. Okay. So it's really simple, but don't forget that impetus is the core of all of this. So there are the ingredients of force, causes impetus, which causes motion. Don't jump from force to motion because you're missing the main ingredient, which is the impetus. Okay, it's easy, but I'm going to give you this exercise on the test. Just explain it. So there are other situations, like you could have a mass on the end of the spring, for example. And suppose the spring has an equilibrium length where if it's at that length, it's neither stretched nor compressed, so there's no force from the spring. So now if I stretch, so there's an equilibrium point, if I pull the mass off to some side, the force that pulls it back gets stronger and stronger the farther away it is from the equilibrium point. So now the force is not steady. The force is changing the position. So if I pull it over here, hold it and release it, there's a force that's pulling back. The spring is pulling it back. So but it starts with no impetus. So it's gaining impetus now, moving to the left. But as it moves now, the force is diminishing because the spring is not stretched as much. So when it reaches this point, there is no force acting on the body, but it has impetus. So it continues to move to the left. It overshoots the equilibrium point. And now the spring is being compressed. And as it's being compressed, it's pushing back to the right. So as it's pushing back, it's taking out some of the leftward impetus. And so finally it has no more leftward impetus and comes to rest. But the spring is pushing still. Rest. It's going to give it rightward impetus. So it starts moving back as a result. And it reaches this equilibrium point now with the spring, because it's not compressed anymore, the force has gone to zero. There is no force. It's got now impetus, so it overshoots. So this is simple harmonic motion that we're describing in these basic terms. And why something will just oscillate like this, as long as there's no friction. Okay. All right, now we can also talk then about kinetic energy. Kinetic energy is important because it is the first example of energy. In fact, all other forms of energy that we talked about are spoken of in relation to kinetic energy. And this is another example of what's called analogy. Lots of analogies in physics, in science, because there are analogies in nature. So an analogy is having multiple meanings of a word which are tied back to an original meaning, a primary meaning. So BP is healthy. BP's hair is healthy. Don't mean it in exactly the same way. You don't mean healthy about her hair like you mean about her. BP's diet is healthy. You don't mean it in the same way as that she is healthy. This is analogy. The different meanings of healthy, the secondary meanings of healthy, all point back to the original. So this is the primary meaning of healthy. The person is healthy. Talk about her urine is healthy, or other things. They're all pointing back to the primary meaning. That's what's happening with kinetic energy. Kinetic energy is the first example, the prime example of energy. How do you know? Because you've talked about potential energy in other classes. When I let go of this thing, we talk about potential energy, right? How do I know it has potential energy? Well, it becomes kinetic. can see that it has potential energy when it starts to do something, when it starts to move. So kinetic energy is the prime analogy of all other forms of energy, because how do you find out that it has other forms of energy? It makes it move. Chemical energy, well, it blows up. You get an explosion or it heats up or something. Even the heat is a kind of form of internal kinetic activity. Okay, so kinetic energy. So to explain kinetic energy, I like to make a comparison to transporting a big pile of sand from the site where you get the sand to the construction site. How would we do that? Well, we use different conveyances. So how about a wheelbarrow pushed by somebody? And then you could use a teaspoon instead. Somebody walks it 1 teaspoon at a time. You could get a dump truck. You could get a Ferrari. Different conveyances. Ferrari has a little tiny trunk, can't get a lot of sand in it. The dump truck's got this big load it can carry, but it goes much slower than a Ferrari. So how do you determine what's the fastest means of transporting the sand? It's a combination of speed and load. The rate of transport is a combination of how much you can carry each time and how fast you can go. All right, so now with this hockey puck that's sliding on the ice, how much momentum is being carried? That is the rate of transport of the impetus itself. Okay, so the load is how much impetus it has, measured of that is momentum. So the load is P. And what's the speed? Faraday law. The speed is the momentum divided by the mass, E over M. Pretty close. So this is P squared over M, or it would be, I guess, MV squared, right? If you wrote it in terms of P, it's P times MV, so it's MV squared. So it's pretty close. There's a factor 2. What's the factor 2? The reason for the factor 2 is that unlike the dump truck or the Ferrari or the well, maybe the wheelbarrow would be, but the dump truck and the Ferrari, the speed is not determined by how much sand it's carrying. But in the case of massive bodies like this hockey puck, the more impetus it has, the faster it moves. So you've got a combination of 2 effects. If you give it more impetus, the load increases, but so does the speed. You have to use calculus to figure out this variation. There's an extra factor of 1/2 here from doing the calculus correct. So you get 1/2 because the speed is varying with the impetus. So the load is changing and the speed is changing. So that's the 1/2. Okay, so that's kinetic energy. Kinetic energy is the rate of transport of the impetus across a distance. It's a different kind of measure of kinetic activity than momentum. Because momentum has a direction, and kinetic energy doesn't have a direction. It's a scalar in that sense. In the sense that if I have several parts of a substance or several substances in a group, and I add the momenta of each one, then I get a vector sum. Could cancel out. The total momentum of a system can be 0, but it can still have activity. And so the kinetic energy is a different way of accounting for that because it helps to account for internal activity within a system. So whereas the total momentum may be 0, some of the kinetic energies might not be. And so you can account for the activity within a system using the kinetic energy. So it's another way of accounting for kinetic activity. So you could have the total momentum of the solar system being 0, but might have some kinetic activity. Certain things are moving around, so the total kinetic energy. Okay. Any questions so far about this? Yeah, I'm still working on the names. I'm sorry to drag you through this, but I want to know your names. Sorry. Okay. Remind me. Oh, the birthday boy. Mr. Silva. I don't remember you now.
is kinetic energy, would kinetic energy be a quality of something then? Or is it still,
Yeah, it's a measure of the impetus, a different measure of the impetus.
so is pretty much everything like we've been talking about, kind of a different way to relate impetus to
Yes.
how we can like actually use it?
Yes.
Alright.
So if you were going through the first semester, you would also learn about, for example, angular motion, rotation. You would understand that that is not something separate from impetus. It's a different way of accounting for impetus with respect to a reference, point of reference. But it's very helpful to describe rotation, but the cause of that rotation is still impetus. So we talk about angular momentum, it's really not something different than momentum. Or more precisely, it's still caused by impetus. That's an example, another example. Other questions? Okay, so we talked about gravity. So let's go back and look more at gravity. How does gravity work in these basic ways? Well, first we have to establish something. What's between my hands? Okay, if you haven't read it yet, what would you?
Space.
Space, okay, space.
Air.
Air. Okay, let's get rid of the air. Hold your breath, we'll evacuate the room, right? Okay, hold your breath. It's not air anymore. What is it? Space or vacuum. But those aren't very descriptive words. In fact, somebody might say, nothing between your hands. But that wouldn't be correct. Nothing is not right. Now there's nothing between my hands. There is something between my hands. I can look through it. I can see you through this. Gravity propagates through it. It isn't nothing. In fact, let's think about this a little bit, about what we mean by nothing. If I say sound and I say silence, those two words are related to each other, but one describes something that exists. The other one describes an absence. Silence is the absence of sound. It's not an existing thing, but sound exists. How about light and dark? Same sort of thing. Light exists, but darkness is an absence of light. It's not an existing thing. Where does nothing fit?
It's the absence of something.
It's the complete absence of being. So nothing is in this category of absences. These are not existing things. In fact, nothing cannot exist. By its meaning, it's non-existence, so it can't exist. To be precise about it, the primary meaning of nothing means nothing, right? It can't be something, it can't exist. I mean, if you're trying to use the word nothing, you can only use it in ways that kind of deviate from this primary meaning. Okay, so space and vacuum are more like nothing in our minds. When we use these words, we're talking about an absence of air in the case of vacuum. Space, though, space is a little nebulous and confused, right? So let's talk about space for a minute. Let's imagine, we've got lots of different substances in this room, and you are some of the substances that exist in this room. Let's one by one start taking away properties of the substances that exist in this room. Let's take away time. So don't move, can't change. Right, but there we go. How about environment? Well, we take away all the environment of the substances. Take away, we stop even thinking about action and reception. We take away all the qualities, all the color, all the temperature, all the texture. All that's left is quantity. We've stripped everything from you except your size. And we don't even really think about the parts, how they relate to each other. Just have the quantity. That's kind of what we're doing with this word space. Space is kind of, again, a confusion about something. Planet exists, it's real, but we tend to strip away properties of the planet and think about it just as extension. And that's it. That's what we've done with this space. So space, a better word to talk about what's between my hands is the word that is introduced in the reading, which is planet. Planet is a substance. It's not massive, so it's not like a hockey puck. It doesn't move in the way that hockey puck moves. It's different. It's a different kind of substance than that. It has properties. It has extension. The distance between my hands is the extension of the planet that's between them, between my hands. It has lots of properties. The name, in fact, is chosen to reflect that one of the basic aspects of planet is that it hosts fields. It has in it properties which we call fields. So gravity is an example of a field, which is a property of the planet. It's a quality of the planet. An electric field, a magnetic field, these are properties of the planet. Light is a property of the planet because it's an electromagnetic wave. So these fields propagate from one part of the planet to another. So it would be, you would say then that in this planet, that there is a field that exists here generated by the Earth that propagates away from the Earth. Now, what's the speed of that propagation? Well, it's not easy to tell, but it's the speed of light. Gravity propagates at the speed of light. It's hard to prove that, but we know that it does now. But that's something that's takes a lot of experimentation to determine that there is this speed of propagation of gravity. We call it the speed of light, but it's also the speed of propagation of fields like gravity. Also electricity and magnetism, which are of course related to light. Okay, so there is this propagation that occurs. Okay, so now we have something, then an aspect of the Earth which causes it to generate in the planet around it, a field, a gravitational field. And this is then called the active gravitational mass. At first, there's no reason to suppose that it's like the mass we were talking about before. So the mass we were talking about before is called the inertial mass. It has to do with locomotion, and it's the resistance to the impetus. At first blush, there's no reason to think these are related to each other, even though we use the same name. So the active gravitational mass changes the planet in its vicinity and keeps changing the planet in its vicinity. And the planet with this field propagates that field outward. If by some unnatural means you can get rid of the Earth, the field that had been generated by the Earth would continue to propagate outward. The news about that would take some time. So if the sun somehow by some unnatural means was just erased, it would take us, what, 8 minutes? We would still see the light that had been emitted before it got extinguished. We would also, the Earth would continue to move in a circular orbit around the sun. The force of gravity would continue to pull the Earth towards the sun, even though the sun's gone away. So that propagation takes place. The fields propagate through the planet at the speed of light. Okay, so let's suppose I have now, here's the hockey puck, here's the Earth pulling down on the hockey puck. How does it do that? Well, the planet that's activated and has this field in it reaches the hockey puck. Doesn't take long. Reaches the hockey puck. Now, the hockey puck has what's called a passive gravitational mass. Passive in the sense that it receives, it's the receiver. The action and the reception. So the passive gravitational mass, when the planet has this field present in it, it exerts a force on the passive mass, which directs it, the force is directed back to the Earth. It's always attractive. Gravity is always attractive, never repulsive. Okay, well, meantime, the hockey puck is altering the planet around it. It has a field that's producing, it contributes to the field in the planet. And that's propagating back. Also, there's part of that's propagating back. And the hockey puck exerts a force on the Earth. So those bodies have active and passive masses, gravitational masses. And it turns out that these two forces are the same magnitude. The hockey puck is pulling up on the Earth just as much as the Earth is pulling down on the hockey puck. It's just that the Earth is so big, you don't notice that effect, but you can notice the effect that the Earth has on the hockey puck. Okay, so 3 different kinds of mass that we're talking about: inertial mass, passive gravitational mass, and active gravitational mass. Very peculiar thing, must be confirmed by experiment. In principle, they're all different. But empiriometrically, you could use the same measure for all 3. Why is that? That has to do a lot with Einstein's general theory of relativity. And but in principle, they could have been different. But empiriometrically, we can put them all to be the same. And so when this body is being pulled by gravity, the force of gravity is proportional to its mass. And the resistance to the impetus is also proportional numerically to the same value. So the effect is that 2 bodies with different mass will fall in the same way. The force on this one with the larger mass is bigger, but its resistance is bigger. And so the change, the difference, because of the mass being different, cancels out in a way. And so they fall in the same. It's very peculiar. Okay, well, I can do the same thing with electricity. Let's suppose I have a charged body. So, 2 different kinds of charge, not in the way that you're used to thinking about it: active charge and passive charge. Active charge generates an electric field in the planet around the body that propagates outward at the speed of light. And that's received by a second body, which must also have passive charge in order to receive the force. Difference is, now there's 2 different kinds that way, but there are also 2 different types of charge. So the 2 different types, if these have the same type, we speak in terms of plus and minus charge, but they're just 2 different types. If these 2 types are the same, the resulting forces are repulsive. If the 2 types are opposite, then the forces, or if they're of different types, then the forces are attractive. Interesting, very similar to gravity, with that difference that it can be repulsive. And that there's 2 different kinds of charge, which we refer to as positive and negative. Okay. So pretty much what I want. Questions about that, how force works, this kind of mediating force, yeah.
Kind of a two-parter, does everything under the scope that we've been looking at have Plana, basically?
Say again about fauna?
Does everything have Plana, pretty much, like,
Yeah, as far as we know.
and then does it have to be between two things, or can it just be like an infinite kind of? Can Plana be infinite, or does it have to be like between like the two hands? Like we talked about?
No, I don't think it can be infinite. But I'm not sure quite what you mean by that.
Like, if I take this hand down, is there still Plana, or is it just?
Oh, yeah, there's still, if you're holding up your hand, there's fauna. If you take your hand down, there's still fauna all around, right? It's the non-massive substance that's between all massive substances. We don't know the edge. You've never seen an edge to it. Don't know about that. That we don't know. Yeah, Mr. Nazarian.
Yeah, my question's kind of big, doesn't need to be answered, but like, the universe is like expanding into like a void. Would you call that the fauna?
I guess we don't know, right? So one of the tasks of physics is to find out what's there, and we just don't know yet. So I don't know the answer to that question about what's beyond what we can see.
That is a good question, but is it referred to as like a fauna or?
Well, you have to find out what's there. Yeah, you have to, and it's hard for us to do that. Well, it's plausible. I mean, I don't know. I guess you can imagine different kinds of scenarios, but you have to be careful with your imagination. You need to go find out, to be sure. And that's an important point with this textbook. Dr. Rizzi talks about levels of abstraction. And also levels of specification. There's a lot about fauna we don't know. And it's important not to become too specific too fast. You need to understand and bring in evidence about the thing before you determine that it's specific. It's specific properties. And an important point of that happens in electricity and magnetism. When Maxwell was developing his theory of electromagnetism, he recognized that some of the equations that came out look like propagation of sound in a medium. And so he thought, well, maybe that light, specifically the equations for light, resembled the equations for sound. And so he thought there must be a medium for light. And so he called that the ether. But the problem was he went too specific. He was correct that there had to be something that the light was propagating in, property of the fauna. But he went too specific. He said that it had to be, in fact, some vibration. It had to be a massive medium. And that light was vibrations in the medium, like sound is a vibration in the ear. That's wrong. That's not correct. And it's an example of going from general to specific too fast. Bringing some specific that isn't really called for by experiment. And that's an example of that. We can say certain general things about fauna, but there are other things like, is there an edge to this? Don't know. You can speculate, but you got to remember it's speculation. You really want to bring in evidence to determine something. I could say there's a little green man sitting in that chair, but until I have evidence for it, there's not really much reason to do that. So that's what we need to do, is go very careful and not become overly specific too fast. Understand certain general, we understand certain general principles. Okay. Let's see, I guess I'm just about out of time. The fauna is going to come back quite a bit, as well as massive bodies, because we're going to understand the structure of the atom. Okay, now the ironic thing is here I'm teaching you very general principles that we learn from things that we sense, we know. And then in this course, we're going to start talking about atoms that we don't know very well, right? You don't know them. I don't have much personal experience with atoms. Not on the scale at which we're talking about, the internal structure of substances. That's not something that we have a lot of good experience with. And so it's unfortunate because we should have spent a whole year for you to get these basic principles down, learning about how things move, how they rotate, how bowling balls go, and then electric fields, magnetic fields, and light, and all that stuff. You had good experience with it. You've had that behind you. Then we're going into atoms using that knowledge. So we have to be careful. And when we get to chapter 1 in the book, which is coming up next week, he's going to review the experiments about 100 years ago that started giving evidence that there was some kind of new physics that wasn't present, you didn't understand in Maxwell's day. And so it's very careful, it's very important to review the experimental evidence. You don't have personal experience, it would be best if we had a lab for this course where you could go in and do those experiments yourself and really learn what they were about and really even build them. That would be great. But we don't have that. So you're going to have to watch some videos and look at some plots and things. Right? But the best thing is for you to have your own personal experience.
What was the prerequisite for this class?
I'm sorry, say again?
What was the prerequisite for this class?
I can't hear you very well.
What was the prerequisite for this class?
What's the co-requisite?
Yeah, I thought there was a prerequisite.
You mean lab?
Yeah.
There might be a lab. I mean, there has been one. The department went through a phase where they weren't offering it. Now I think they're back to offering it.
Oh.
But it's
There was no lab in that kind of computer.
but it's not well synchronized with this book.
I know it's a different structure.
And there is a graduate student who's working on that. But I don't know what they're doing. If they're offering the lab this term, I don't know what labs are doing. They may be related to atomic physics in some way, so it might be that you get to do some of those. But my whole approach to doing labs is get rid of black boxes as much as possible. You ought to understand everything about the apparatus that you can. Or when there's something that's special that's a black box, at least you acknowledge that it's a black box. You don't know how it works. It's really important for you to understand all of these steps that are involved in doing the experiment. And unfortunately, we can't do that all the time. So we have to compromise sometimes. But I'm going to do some demos here in class. And the guy who helps me with the demos, I'm always telling him, get rid of the black boxes. I don't want black boxes. I want as few black boxes as possible. I want everything to be visible to the students for watching the demonstration and know what everything is. You don't have any special meters and things that are measuring things. They don't know what they're being measured. So it gets harder when we're doing atomic physics. It's great when we're doing E&M, electric fields, magnetic fields, people have a lot of experience with those. It's a lot easier. Now we're getting into the atoms, it's harder. So we have to work on that. But anyway, we're making progress. Do you have a question?
Not necessary. Sorry, just scratching my head.
Figuratively speaking. Ken. Scratching your head. All right. Any questions?
I would like to talk to you after class.
Okay, yeah. All right, so we'll see you on Monday.